Well, thank you very much. It's a pleasure to be anywhere at my age. I look around and see I'm probably the oldest person here. I'd like to, there we go. As always, first side disclaimer. I'm still a consultant for Microport Orthopedics. I still have a little bit of royalties from the revision knee. My own company is called EVA 15 LLC, and I'm an emeritus professor at the University of Michigan. All the IP in this presentation belongs to me, except that's been sold to Microport. An Odyssey is a long or wandering voyage marked by many changes of fortune, and that's exactly how we've been in the medial pivot. My Odyssey in orthopedics started at the University of Michigan, where I went to medical school, then did a general surgery residency, as was required in those days, and then an orthopedic surgery residency. At the University of Michigan, we learned that there are two ways to do orthopedics, the Michigan way and the wrong way. So many of the people trained in that era found the same thing. My first introduction to biomechanics came with Larry Matthews, who just recently passed. And the Bible that we used was the Frankel and Burstein Orthopedic Biomechanics. What I did with Larry Matthews was something that has been supplanted now by computer technology, but we looked at all of the welds on the spherocentric knee with stress coat to see if it was going to be strong enough to withstand the stresses that they'd find in the body. This volume, Knee Ligaments, Structure, Function, Injury, and Repair, has on its cover the 4-bar link and the statement that the kinematics of the knee are guided by the 4-bar link. When I was starting my Odyssey in orthopedic joint replacement, that was the Bible by which we wanted to do any design. The 4-bar link is the anterior cruciate ligament, the posterior cruciate ligament, the femur, and the tibia. And if all of these segments are rigid, the mechanics of this works out that any instantaneous center of rotation or the instantaneous axis of rotation, if you're counting in 3-dimension, must pass through the crossing point, that's I, of the cruciate ligaments. This paper by O'Connor and Goodfellow shows that because the crossing point is anterior in extension and posterior in flexion, it was then dogma that the femur must move backwards on the tibia as the knee joint flexes if the function of the cruciate ligaments is going to be duplicated. That was called, inappropriately since it's not actually rolling, but it was called rollback, and rollback was absolutely necessary. You can't prevent rollback. So when knee components were designed, the ones that I worked with the most, the dogma was that the knee is symmetric. Both sides of the knee work the same way, and the cruciate ligaments guide the knee so that the femur has to move forward and backward on the tibia. The 4-bar link's not actually taught anymore, I see to the residents, but most of what we think about knees still comes down from and is descendant from that idea. This is an interesting white paper presented by John Insall through the Zimmer Company. This white paper said that after the cruciate ligaments have been excised, that is in a cadaver knee, looking at how the knee moves, after the cruciate ligaments have been excised, the collateral ligaments are of equal length and equally taut in extension and 90 degrees of flexion. That's what Insall taught. That Insall taught that the knee joint is symmetric and the medial and lateral collateral ligaments are equally taut in extension and flexion. His technique shows what he thought. First of all, he resected the tibia at right angles to its long axis. Then he placed a rod up the femur with handlebars on each side, and he said he put his strongest resident pulling up on those handlebars, and what he wanted was for the knee to rotate, and he said this is the way a normal G should rotate. And I don't have a pointer, but you can see that when he was the way he thought it should be normal, the same amount of bone is showing. The same amount of bone would be cut from the posterior cut. We know that's not the way the knee joint really is, because the epicondylar axis goes like that. And so when the knee joint rotated like that, which we now believe is the way it should be, Insull said this is an apparent contracture. And what he wanted to do was to release the ligaments until he could get back to the point that the knee joint looked symmetric. He came with the idea that the knee joint was symmetric. When he saw something that didn't look symmetric, he said, I need to change things to make it back to symmetric, because his bias was that the knee joint was symmetric. Prosthetic joints at that time were symmetric. In this case, the geometric. Both cruciate ligaments are retained. It's fully conforming. And it had a high degree of loosening. And those people who believed in the 4-bar link said the reason why is because you have prevented the forward and backward motion. And because you prevented the forward and backward motion, the knee got loose. Hinges had problems with getting loose too, so they said, well, that was another thing. You don't allow the forward-backward motion. So loosening is because of not allowing the forward-backward motion. And so the rationale was that we should now make the knee joint non-conforming so that you don't prevent the forward and backward motion of the femur on the tibia. The rationale going, 4-bar link rollback is obligatory, rollback in conformity reaches kinematic conflict, conformity equals constraint and loosening, and non-conforming, that is unconstrained, leads to no loosening. So we see here the ligaments, the components were made so that there was no conformity between the femur and the tibia, so that you wouldn't have a kinematic conflict with the 4-bar link. To provide for stability, the concept of ligament balancing came in, and that is trying to tighten the ligaments so that the ligaments guide all motion of the knee. If you have conformity, you have loosening. If you don't have the ligaments tight enough, the knee joint will be unstable, so you need to tighten the ligaments, and that was ligament balancing. These are the components that we use in residency. You can see all of these. The spherocentric was the hinge. The rest of these were all ones that would require ligament balancing. My next stop was the London Hospital in London, England. The practice of arthroplasty was changing considerably, and I gained some experience both in England and around the European centers. And in conversation with my mentor, Michael Freeman, sitting in the T-bar, rolling up our pant legs and watching our knees, we concluded that the knee joint does not roll back. We concluded that the medial side stayed stable. And after that, I made the idea that perhaps the 4-bar link was actually sloppy. Little did I know that that was actually stupidity, engineering terms, because if you don't have rigidity in 4-bar links, it doesn't work as a 4-bar link. But nonetheless, I came back to West Virginia, and I began to investigate the motion of the human knee. Well, I'd like to go back. There we go. That ended up in a PhD dissertation. I inherited a PhD student from a faculty member who had left. And from that, we also published a paper, The Kinematics of the Human Knee Using an Open Chain Model. And this is where this research work that convinced me that perhaps the medial and the lateral sides move differently. This was our research setup. We basically pulled on the quadriceps muscle. We had some asymmetric loads left on the medial and lateral hamstrings, and we followed the tibia's progress around the femur. We presented our results as the instantaneous axis of rotation. And each one of these black lines on this represents an instantaneous axis of rotation for the femur moving around the tibia. On the far side of this, the larger circle is the medial condyle, closer to the lateral condyle. And you can see that these instantaneous axes of rotation go through the center of the far condyle. But you can see the piercing point is between the center and the surface on the lateral condyle. That indicates there's difference in motion. And we defined this difference in motion between spinning and rolling. If the instantaneous axis of rotation went through the center of the condyle, we defined that as spinning motion, like a tire slipping on ice. And we gave that a number 1. If the instantaneous axis of rotation was at the surface We define that as rolling, as this tire rolling down. So there's two different motions of this tire, one sitting still, spinning, one rolling down the hill. We graphed our results for the medial and the lateral condyle and showed that the medial condyle remains in spinning kinematics. That is, that the medial side spins, the center of rotation, or the axis of rotation in 3 dimensions, is largely near the center of the condyle. The lateral side starts with rolling, then it does a combination of rolling and spinning, and then it actually goes in the opposite direction. The lateral side does not move the same way the medial side does. The knee is asymmetric. The dogma that the knee is symmetric is not correct. This is where we did both extending knee and flexing knee, both with increased hamstring loads, medially increased hamstring load. Laterally, you can see that there's a pretty significant difference in what the lateral side does, but the medial side stays in spinning kinematics throughout this whole experiment. So we can conclude from this that at least in this experiment, the knee joint does not move as a 4-bar link. There is no rollback, but progressive internal rotation makes the femur on the lateral side move backward. This is not rollback, it's actually axial rotation of the tibia along a long axis. If you have a disc, if you have an object that has a disc on one side and the disc on the other, and one side rolls and the other side spins, the object will turn on the surface. The far object is spinning, the near object is rolling, and so this is a definition of the rotation of the femur. Pinskerova and Freeman found the same thing. If you see this stop-action video of MRIs done by Vera Pinskerova, the medial side is staying in spinning kinematics, whereas the lateral side is doing just as our model said, a combination of rolling and spinning, moving to the back of the tibia. This led to the idea that the medial side of the knee is actually a shallow ball and socket joint, while the lateral side, the convexity of the lateral side, means that it's 2 discs rolling over each other. The motion is different, the shape is different, the knee joint is not symmetric. This led to the idea that the medial ball and socket joint should be the next design of an artificial knee. And at the advance meetings, the advance was the prosthesis that preceded the evolution, my big contribution was to continue to complain and continue to request that the condyles be made spherical, so that the condyles could be contained by a ball and socket joint, and that allowed the knee joint to be a medial pivot joint. I was told that it was a bad idea. I was told that it was a stupid design. I was told that it was a disaster waiting to happen. And I can remember Tom Thornhill telling me, wait till you have to revise them all. At first, I recommended putting the prosthesis in like others, mechanical alignment and ligament balancing, but I had frequent manipulations. I then recognized that the ligaments to the knee are loose in flexion. They're tight on extension, but they're loose in flexion. Loose ligaments can't guide the knee, but congruence between the femur and the tibia can. So we came to the conclusion that ligaments should be used not to guide the knee. Stability and kinematics should come from conformity. So after 24 years, I don't think it's a bad idea. I don't think it's a stupid design. I don't think it's a disaster waiting to happen. We're at 24 years now, and we still are having good results with the medial pivot knee. And I haven't had to revise them all. Now, many companies are touting their medial stabilized design. And I point to this quote from Schopenhauer. It's not actually the German, I actually read the German, but it comes close. All truth passes through 3 stages. First, it's ridiculed. Then it's violently opposed. And third, it's accepted as being self-evident and always was true. That's where we are with the medial pivot. It always was true that the medial side is different than the lateral side. The medial side is more stable than the lateral side, and hence the right design for an artificial knee is the medially more stable medial pivot. Thank you.